Check it out now, y'all.
nanoHUB-U, online instruction.
All right, welcome back. This is lecture 2 of week 1 of the course Thermal Energy at the Nanoscale. The last time we spoke, we went through a general overview of atomic bonding, and it was very cursory, but it was that way intentionally, just to give you a flavor of the types of bonds that exist and kind of what the energetics of the bonds might look like. Now we're going to actually string together a bunch of atoms, and each one of those atoms will have bonds with its nearest neighbors. And so this is an abstraction that we'll use a lot in this course, that is the atomic chain. And we'll just think about one dimension. So this atomic chain can move. The atomic chain can have atoms that move, but they only move in one dimension. So you can kind of think of these as just moving back and forth from left and right. I think we've all seen chains, and we see waves that go up and down, left and right, back and forth. But in this case, we're going to restrict the entire problem to one dimension. So these atoms just move back and forth against each other in that one dimension. And some really important things on this graph will become apparent as we go through it. But that spring constant that we mentioned last time, G, that kind of forms the constant of proportionality between energy or force and the displacement, or the displacement squared. That is really important, and we'll find that the spring constant shows up in a lot of our derivations as we go through. The atoms themselves are separated by a distance, and we're going to call that distance A in this case. So the lowercase a, we'll call that the lattice constant. Now, in some cases, in more complex situations, the lattice constant can actually comprise more than one atom, or it's not necessarily the interatomic bonding distance. It can span across different atoms, and we'll explain why that is when it comes. So I want you to be careful with that symbol A. And the translation vector, that is the vector that I have to move in integer values in order for the lattice to look the same as it did from where I started, we're going to call that a translation vector in general. In this case, in this one-dimensional problem, it's very easy. That vector is just the distance a, the lattice constant a, times the direction x. The last term in this is the atomic mass, and we're going to denote that by lowercase m. There are some more complicated lattices that I think it's useful to look at, right? In this context, certainly graphene as a material has become very popular for a variety of reasons. It has some outstanding electrical and thermal properties, for example, and optical properties. But graphene is comprised of all carbon atoms. So every atom that you see in a graphene lattice is carbon, and it's arranged in this honeycomb pattern where there are groups of hexagons that are linked together in a two-dimensional array. So the last slide showed a one-dimensional array, very simple, just a chain of atoms. This is the most common, or at least certainly the most popular, two-dimensional array of atoms. And here we see some differences, of course. We don't have nearly the geometric simplicity that a one-dimensional chain gives us. Each carbon atom has nearest neighbors, and they are 1.42 angstroms apart from each other. But then, as we start to think about the ways that we can describe this structure mathematically, we see that the lattice itself repeats its arrangement of atoms, not every distance a tilde, that's the interatomic spacing, but rather on some larger length scale. Like if I move in the direction that I'm showing here, bottom to top on the left figure, then it repeats itself every distance 3 times the atomic separation distance. And then if I look at a different orientation, then that distance of periodicity is the square root of 3 times a. And you'll hear often people talk about different edges of graphene, and so here I'm going to try to explain them to you. On the left, we see what's called a zigzag pattern. And so the zigzag, I'm drawing it right now, goes up and down, a fairly small angle here. And then these other atoms here, so this is these 3 atoms that kind of jut out from the zigzag, those are there mainly to passivate any dangling bonds. So a lot of times those atoms would not be carbon, they'd be hydrogen atoms, for example, in real life. But the zigzag edge is the one that I drew originally. The other type of edge is an armchair edge, and that's shown here. And I don't know how much imagination it takes. I think sometimes it takes quite a bit to know what they mean by armchair. So I'm going to draw the person sitting in the armchair. Here you have somebody sitting in the armchair, and then the arms are here, resting on the armchair. So that's the armchair edge. When I first looked at it, I wasn't sure what it meant either, but maybe that's because I haven't sat in any big high-armed chairs before. But in any case, that's the armchair edge. And graphene exhibits different properties depending on which edge is exposed or which edge is aligned to the direction of transport. So it's important to appreciate that difference. If we move to 3 dimensions, and we're not going to do too much of that in this course, there's a lot of great books in condensed matter physics and other courses in crystallography where you can get you can gain an appreciation for a lot of these different factors that go in. It's a very rich and deep subject. For our purposes, we're going to be mostly interested in simple 3-dimensional lattices, and so those would be derivatives of simple cubic. And you might wonder, well, are we missing out on a lot of really interesting materials? And I suppose we would be. So there are many different types, general classes of 3-dimensional crystal lattices that are listed here. I won't recite them to you. But in terms of derivatives of simple cubic lattices, they do include 3 really important ones: body-centered cubic, face-centered cubic, and the diamond lattice, which does not mean that it's actual diamond material. It doesn't have to be all carbon, although that is a diamond lattice. That's why it's called diamond, or the diamond lattice. But many very interesting materials form in these derivatives of simple cubic. So that's body-centered, face-centered, and diamond. Gold, for instance, comes in face-centered cubic is the most common lattice form. Silicon and the diamond form of carbon are in the diamond lattice, and so they're very important. We won't go through too much of the crystallography of 3-dimensional lattices simply because we don't have time. But I think most of what we're going to teach and learn in this course will be reasonably easy to extrapolate to that 3rd dimension. We're going to focus mainly on the 1-dimensional chain, and then we're going to move up to 2-dimensional materials, and graphene will be our surrogate material mainly for 2-dimensional studies, and not so much in the 3rd dimension, but I think that we'll get certainly 90+% of the way there in terms of understanding for what you need to do for 3-dimensional materials. The other factor, aside from those perfectly well-ordered crystals, is that most real materials are not single crystal. Most engineering materials are not single crystal, and so they have defects. These defects can come in many different forms, and again, we won't go through all of the different possibilities of types of defects, but certainly one of the most common types of materials that's important technologically today are polycrystalline, the class of polycrystalline materials. Here we show on the left how a polycrystalline material is formed. This is the early stage of diamond growth, but this is synthetic diamond growth by a process called chemical vapor deposition. And you can kind of see these different grains, and you see the facets showing very clearly in that triangular form. That means that they have a specific lattice orientation, and then they cluster together to form a polycrystalline material. And those grains are important for many reasons. They influence mechanical strength, for example. They influence, for our purposes, they influence transport properties, and especially thermal transport properties, very heavily. And so we want to understand that these materials do exist, and understand that we're going to have to do something, especially with that transmission of energy carriers, to account for the effects of grain boundaries. So The other class of materials that we really won't have time to spend much attention with is amorphous solids, and they're also technologically important. Glass is the most common one, certainly, but amorphous solids lack any long-range order. They're kind of like this frozen liquid. The atoms are clumped together, and usually they're in a stoichiometric distribution, meaning that there's the right numbers of one kind versus another if you had a compound material, for example. But they do not form this nice systematic, repeatable lattice structure, and so that means that the study of transport in these materials, especially thermal transport, becomes much more difficult than what we will use. And so, because the way that we'll study the problem, we're looking at long wavelengths that can be much larger than the interatomic distance in some cases, and so the study of those long wavelengths requires some long distance, long range order of the atomic structure. So this crystal lattice, let's get back to this. We can construct a crystal by essentially mapping a bunch of points in a systematic way throughout whatever dimensionality of space we're interested in. So the way, when one does that, it's called a Bravais lattice, and that is an infinite array of points whose positions are described by this systematic repeating of locating the points in space through this combination of vectors, that's A1, A2, and A3, and an integer prefactor on those. So these A vectors are called primitive translation vectors, and if we just let the n's, n1, n2, and n3 go through from 0 to infinity, then we would fill all of space. Now, the points that I show here, you'll notice I actually wrote the word point. They're not necessarily atoms. They are just reference points to which atoms are sort of bound, as we'll show in a moment. And so I want you to at least appreciate a little bit of that subtlety, that they're not necessarily atoms. In some cases, we're going to have to cluster a couple or a few atoms around each point in order to make a real material out of it. But this Bravais lattice is important because it kind of gives us a mathematical basis for this periodicity, for this symmetry in real space that we'll need in order to understand and to mathematically describe transport processes. Now, if I look at all of this three-dimensional space, what we'd like to do is to say that there's just a small bit of space that looks like every other bit of space if we just translate it through all the possible R vectors that we showed on the last slide. And we can do that in a number of different ways. In this case, what we've taken is each cell, this is a two-dimensional problem. We could have taken this bottom left region of space and then repeated this. We could have taken one that in which the single point is in the middle of the space S, and then we could repeat that throughout all of the R vectors and fill all of space exactly without any overlap. But we could also take these parallelograms and do the same thing. So the point here is that these primitive unit cells are not unique. You could define them in a number of different ways and shapes, and there are general criteria for deciding which one to pick for different types of lattices, and we won't get too bogged down in the details of that. I told you before that these points in space were not necessarily atoms, and the reason for that is that many crystals of interest to us, some of them compounds, meaning they have two different elements, two different atoms, and some of them single atom materials, they have to be described in this process of this repeated repetition throughout space. They have to be described by something called a basis. So we need to have two or more atoms at every one of those points in order to fill space the way that the real crystal fills the space. So a compound material is obvious. If I have a compound material like copper oxide, then that, by definition, we can't have a copper atom representing an oxygen atom, so every one of the points that we defined in space would have to have a copper and an oxygen. But even silicon, we talked about silicon forming the diamond structure, even silicon requires a basis atom to define the way that it sets up in three-dimensional space, and so silicon actually has 2 silicon atoms for every one of these points in space, every one of these Bravais lattice points. So again, we're not going to go deep into the crystallography. I just want the audience to appreciate that there are many of these nuances that are very important, and we're actually going to show that this basis atom, in a few lectures' time, will show that this basis atom affects the way that heat flows in a material, or at least the opportunity for heat to flow by a different mechanism, a slightly different mechanism, by adding some different kinds of lattice vibrations. So let's go to graphene. That's going to be our favorite two-dimensional crystal lattice. Again, each atom in graphene is separated by 1.42 angstrom, so it's a very small, tight bond. It's a very strong material. I think those who have studied it know that. But even graphene requires a basis atom. We have to have 2 atoms per point in order to describe its structure. And if you don't believe that, I think it's interesting to try on your own to create a lattice that repeats itself and fills all of the true atomic sites without a basis atom. So what we're going to do is we're going to define here the primary atoms. So those are the blue atoms. Those are the primary atoms. And each of the primary atom locations are connected by translation vectors, A1 and A2. And so if we just cycled through integer multiples of A1 and integer multiples of A2, then we would touch every blue point on this space, and we would form our Bravais lattice in 2 dimensions for this material. Now, the green atoms, so every blue atom has a green atom partner, and the blue atoms here the green atoms are always to the right of the primary atom for that cell, for that unit cell. So we have, again, these are pairs here that I'm showing. So it's useful to draw these, and so these 2 are the primary and basis atom pairs, and those are repeated. And of course, the basis atom then is defined by a vector, and the vector for the basis atom, if I had to do that, it would be so this is going to be the interatomic distance times the x vector. So that's how we define the graphene lattice, and it's a little bit more complicated perhaps than you might have hoped, but it's not too bad, and we'll show that that it's fairly easy to study mathematically once you kind of put all of these things together. Speaking of mathematics, one of the things that we're going to do, and we really need to do it, is to transform the lattice from real space to something called reciprocal space. And we'll start to do that today, and we'll use it, and we'll kind of build this into our studies as we go, because mathematically this is probably the thing that trips up students more than anything else. Let me tell you the reason that we do it. We're studying lattices that go off to infinity for the most part, at least in one dimension. And so if we had to include in everything that we did an infinite number of atoms, an infinite number of unit cells, then we would be stuck with really doing a lot of mathematics and a lot of very heavy summations or integrals. If we can somehow invert space, so do what's called reciprocal space, or develop something called reciprocal space, then that thing that goes off to an infinity, think about a wavelength that goes to infinity meters, right? if we can invert that, then infinity, 1 over infinity, goes to 0, and so that's much more manageable generally. Now you might say, well, what about the other end of the spectrum? What about the 0 distance in real space? If you invert that, that goes to infinity, and that's true, except in our case, we're kind of limited. We don't really care so much about distances shorter than the interatomic spacing, because anything shorter than that, really, we're talking about regions of space where there are no masses, for example. And so we can kind of cut off. We actually do have a lower limit of the spatial range that we're interested in, and that would be the distance a in general, the lattice constant. So if we look at how to do this, how to Fourier transform the lattice, so to speak, generally speaking, if we had a chain of atoms, the chain would look like this. We have this periodicity. We're interested in what the density, in this case, what's the mass density as we march along this chain, and as you might expect, it'll look like a bunch of spikes in a row. And if we had, really, if we went deep into the math, we'd say that it looks like a delta function, just a spike of density and then nothing in between those cores, in between those nuclei of the atoms. We're not going to worry about the nuclear details right now. What we will worry about is the periodicity. So what's going to happen is this density function, rho as a function of x, will actually repeat itself. So every distance a, that's the lattice constant in this case, it's also the interatomic spacing. Every distance a, the density is going to look like it did one distance a ago, or to look like it did at position x, no matter what x is. So what we're going to do is we're going to express this density, rho as a function of x, as a Fourier series. So we do that here, and this is, so we'll have these prefactors, rho sub n, and we'll sum. So this is just standard Fourier series math. If you haven't seen it before, it'd probably be worth your time to just read a chapter on Fourier series. It's pretty easy to pick up. Then we do something else here. We say, well, if rho of x can be expressed by this series, then rho at position x plus ma, where m is an integer, also must equal that, because we said above here that those two are equal to each other, rho at x and rho at x plus ma. And so now we'll express that latter term as a Fourier series, and we expand the exponential term. We break it apart into x and ma components, and we see that we're going to now equate these two things. So we'll equate these things term by term. And if we do that, we see that the only way that those things can be equal term by term is if the exponential I times g times m times a equals 1, which puts some severe restrictions on what this gma can be, the values it can take. It has to be 2 pi times an integer in order for e to the I gma to equal 1. So if we generalize this to 3 dimensions, then what we find is that g times r, so r was that Brevet lattice vector that went through all of space. So we have this new term g that comes from our Fourier series, and when I take a dot product of that with my real space lattice vector r, then that must be 2 pi times an integer. So this, you might wonder, well, what are we doing all of this for? Well, what we're going to do is basically say that this vector g is a reciprocal space vector that acts like the vector r, the Brevet lattice vector, in real space. So when we do that, so now we're starting to form a reciprocal lattice. So you can think of r, it mapped around all of real space. This vector g will do the same thing, but it will do it in a different space, in a reciprocal space, where instead of wavelengths, as we talked about before, we will have wave vectors, which are inversely proportional to wavelengths, okay? And so this forms a reciprocal lattice. Again, g is a wave vector that satisfies an equation very, very much like the Brevet lattice vector r, which was composed of these translation vectors a1, a2, and a3. And now these vectors b serve that role. So B, the vectors B, are the translation vectors for the reciprocal space, and they are intimately related to the vectors A, those are the translation vectors in real space, through this relation. Now, we're not going to have to do this very often, but I wanted to present it to you so that you understood, so that you had some background in how these things are derived. I will tell you that most of the math that we do will be conducted in this reciprocal space because the mathematics are easier. Even though conceptually it's more abstract, the math works out much more easily by working with wave vectors instead of wavelengths. And in the next lecture, we're going to talk a lot about those wave vectors. I'll see you then.